Hello everybody, I'm going to talk to you today about potential energy diagrams and how they describe a reaction. So let's talk a little bit about what's happening during a reaction first. So here are two reactants, and collision theory tells us that these reactants have to collide in order to react, in order for bonds to be broken and new bonds to form. Not only do they have to collide in the right orientation with the right amount of energy. If they don't, then they're not going to form a new bond. And you can see in some of these scenarios that I'm showing you here that they're just bouncing off each other and not reacting correctly, where we have a new product. Okay. Eventually, though, what we'll get to is a scenario in which they collide and new bonds are formed. Old bonds are broken and new bonds are formed. So let's take a look at that scenario a little closer. We have the reactants. You can see there's this gray and orange. Atoms are connected into a compound. They come together, and when they react, this is called the activated complex, when they are all together. This is when the potential energy of the system is at its highest, and we'll talk a little bit more about that in a little bit. All right. And now, after the activated complex, we could either go back to the original orientation or we could form new products. And that's what's happened in this case. So to summarize, we have the reactants. They come together in the correct orientation with the right amount of energy, and they form the activated complex. And then you can make the products. And this is what it looks like, a potential energy diagram. The potential of the reactants over on the left, as they react, their potential energy gets greater, the activated complex forms, and you can either go to make the products or you could go backwards to make the reactants. Let's take a look at an example of this and take a listen to what this guy tells us.
When two molecules like hydrogen and chlorine approach each other on a collision pathway, the potential energy between them rises. This is due to the electrons on the outer edges of the atoms repelling the electrons on the outer edges of the other atom. As the molecules approach each other, they will slow down. The potential energy rises, and as they reach the peak of the curve, the moment of decision for the reaction occurs. If the molecules react successfully, then old bonds break and new bonds form, and the products separate, and the potential energy falls down the right side of the curve. If the reaction should be unsuccessful, then the reactant molecules bounce off of each other and they return down the potential energy curve from where they came. The progress of reaction axis could be called time in the case of the successful reaction, but since time cannot be reversed in the case of this unsuccessful reaction, that label would be inappropriate. So the axis is labeled progress of the reaction.
All right, so that is how a potential energy diagram is created based on how the reactants are going to react or not react. So let's look at some other parts of the potential energy diagram. So we can have a reaction move forward, or we can have a reaction move backward. So the products could go back and create the reactants. Not all reactions are reversible, but some are. And this can describe that for us. So the reactants for the forward reaction, the potential energy, would be right here at the beginning, like we saw on the previous diagram. Now, the products for the forward reaction are at the end, all the way at the end. That's if we make the product. And the activated complex, like I showed you before, is when those atoms have come together or molecules have come together, and they could go either way. That's the activated complex at the top. Now, to get to the activated complex, we need to add energy to the system. And in this case, we need to add as much energy as it takes to go from the reactants at number 1 up to the activated complex. So the activation energy for the forward reaction going from left to right is number 4 right here. And you can see that we have gained a total of 150 kilojoules because we started at 100 and we got to 250. So we've got 150 kilojoules added from the reactants to the activated complex, and we call that the activation energy. We want to activate this reaction. Now, the delta H, or the heat of reaction for the forward reaction, is the difference from the difference from the reactants to the products. So going from number 1 to number 2. Which one of these scenarios shows us going from the level of 1 to number 2? Well, it's right here. And you can see the arrow is pointing downward. We go from the top to the bottom. And in this case, the forward reaction, the delta H, or the heat of reaction, is negative 50 kilojoules. And this is why it's an exothermic reaction, which we'll show you in a little bit too. Now, if we want to have the reverse reaction occur, we have to get from number 2, where the products are, or the reactants for the reverse reaction, and we have to get all the way back up to the activated complex. And in order to do that, we have to have an activation energy that's a little higher than we did before. And so that would be right here. And we've gone up a full 200 kilojoules in order to achieve that reaction, the reverse reaction. And then, of course, the heat of reaction for the reverse reaction would be going from number 2 to number 1. And so that's our last little spot. And those are the different parts of the potential energy diagram. Now, an exothermic reaction starts at a higher potential energy for the reactants and ends at a lower potential energy for the products. And you can see that if you took the reactants and you subtracted this amount of energy, you get where the products are. And so the delta H is a negative value. On the flip side, an endothermic reaction starts at a lower potential energy for the reactants and gains the energy for the products. So that's an endothermic reaction, or energy going into the reaction. And we can see this using table I. Table I gives us some values for different reactions. And let's zoom in on a spot. You can see that you've got negative 483.6 kilojoules per mole here. And then if we look at a positive one, we've got positive value right there. And we can go to the bottom here and we see that the delta H values are based on molar quantities represented by the equations. And then a minus sign indicates an exothermic reaction. So if we look at our exothermic reaction, a minus sign going down, and an endothermic reaction will have a positive sign, and it will be going up from the reactants to the products. And that is potential energy diagrams in a nutshell. Have a great day. Bye-bye.